Hello, everyone. I am Michael Buchwald, and I am the team leader for Aerodynamics of Star Wars spacecraft and starfighters. So, first today, I'll be beginning with the background. As an introduction for the group, as I mentioned, I am the project leader, Michael Buchwald. Ben Kazezebek is the project coordinator. Andrew Alquist is the programmer. Calvin Bueller is the lab technician, and Logan Miles is the quality manager. The key components of our research project are specifically the key question we're asking, which is which Star Wars spacecraft would be best suited as an aerodynamically as a radio-controlled or RC aircraft. The key objective that we are trying to find is to experimentally determine the lift and drag of various different Star Wars spacecraft. Some quick background of Star Wars spacecraft as in terms of RC aircraft. The current state of Star Wars RC aircraft is primarily being implemented by Airhogs, which is an RC toy company. In 2015, they produced the X-Wing, TIE Fighter, Speeder Bike, and Millennium Falcon as aircraft, either being RC planes or drones. Currently, in like a research sense, there are no significant or any studies on the aerodynamics of Star Wars spacecraft. The significance of our project is that the more aerodynamic an RC aircraft is, the more cost-effective they can produce the toy for. As some impacts along the same lines, the more cost-effective toy, the more children that are able to use and play with the toy. For relevant equations and theories, we use standard aerodynamic equations with using the force balance to get data from the models. The models we used were for the TIE Fighter, the Delta 7 Jedi Starfighter, the Mandalorian Gauntlet, the Laddie, the X-Wing, and the N1 Starfighter. Our control model was the Cessna 182, which we used to compare our results to real-life lift and drag equations for aircraft overall.
In order to determine which of the Star Wars spacecraft were the most aerodynamic, the following steps were taken. First, a set of 6 different models based on various spacecraft from the Star Wars franchise, as well as a control model based off of real-life aircraft, were 3D printed using the makerspace. The models chosen for testing were an X-Wing, a TIE Fighter, a Delta 7 Jedi Starfighter, the N1 Starfighter, the Mandalorian Gauntlet Fighter, and finally a Laddie transport ship. The control aircraft that was used was a Cessna 182. In addition to changing the model, the angle of attack of the model within the wind tunnel was also changed, using a counter on the force balance setup. LabVIEW VI was used in combination with a force balance wind tunnel combination to record measurements of lift and drag. From these measurements, the coefficients of the two characteristics were calculated and then plotted against the angle of attack. With these new plots, each curve was then compared to one another. The purpose of this experiment was to determine which of the tested models was the most aerodynamic in order to make RC vehicles of this nature in the future. Due to this RC aircraft's nature, several assumptions about the flight conditions were made, including standard atmospheric conditions, as well as assuming the aircraft was flying at a velocity of 35 miles per hour. With the conditions of this experiment in mind, this type of test coincides with the test performance type. For this experiment, the parameters that were changed during the tests include the models tested, as well as the angle of attack that the model was set to within the wind tunnel. In order to get the data from the force balance, LabVIEW VI was used. This software receives signals from the force balance and displays them in terms of millivolts, which were then converted to newtons. For the design of experiments, we chose both the model type as well as the angle of attack, and then decided what we expected each result to be. As you will soon see, these results drastically differed from what we confirmed in our experiment.
During the test, we first derived zero value for the wind tunnel by getting the weight of the model on the lift sensor and the weight of the model as it pertains to the drag sensor, and we used that to zero our data. Then we converted these millivolt values to newtons using calibration derived during our experimental testing. Then we could use that data to calculate our coefficients, where L and D are the lift and drag in newtons, rho is the air density in kilograms per meter cubed, V is the airspeed of the wind tunnel in meters per second, and S is the major dimension of the model, which was typically about 202 millimeters. Our data, as we found using these equations, is shown here on our CL versus angle of attack and CD versus angle of attack graphs. A couple of things are very easy to see off the bat. First off, our X-wing was noted to have the highest coefficient of lift, with the TIE fighter having the lowest coefficient of lift. And conversely, our TIE fighter had the highest coefficient of drag, and our Delta 7 fighter had the lowest coefficient of drag. Using the graphs of coefficient of lift and coefficient of drag and the values associated with each one, we were able to derive L/D ratios for each aircraft at the selection of angles of attack. As you can see, the X-wing significantly outperformed other aircraft in lift over drag, and the TIE fighter, shown in light blue, had very underwhelming performance for lift over drag, a reasonable expectation given its shape. Each spacecraft was then ranked as it pertained to CL, CD, and L/D scoring, with CL and L/D having higher numbers be desirable and a lower CD being desirable. X-wing had the highest CL and L/D scoring, and Delta 7 had the highest CD scoring. This resulted in X-wing being the most efficient aircraft as per our metrics, and TIE fighter performing worst in all categories.
The conclusions that we drew from this project were that the best spacecraft was the X-wing and the worst spacecraft was the TIE fighter. This implies that the next wave of Star Wars RC aircraft should include the X-wing and should also probably not include the TIE fighter due to the fact that it has a very high drag to lift ratio. Our assumptions were that we had a wind speed of 15.62 meters per second, which was calculated from the millivolts on the wind tunnel. We also assumed that calculating CL and CD based off of the major dimensions were done because the wing areas were weird on a lot of our planes. Specifically speaking, the Gauntlet didn't really have wings per se. It was more just a flat body like the Delta 7. Our models were accurate in size compared to the CAD models, which was also pretty good. Mounting method does not have any effects on the results, which might be true, might not be, but the way that we did it, we assumed so because it wouldn't have much, and no wall effects of the wind tunnel were present. For the error, we assumed that 34.3% there was a 34.3% error on the Cessna. We based that off of official information we found on their website, and we used that to calculate CL of 0.2995, and for the model, we found it to be 0.1967. For our error propagation of our results, we found an error of 0.998%, and we found this we didn't find this from the equations because the equations we used did not have an attached uncertainty value. So all of our uncertainty came from our measurements, which were all digital. So the last decimal place of all of our digital measurements for lift, it was 0.00, 0.01, and onward for the rest. We've used those to find the error of the CL value for lift, for example, and we used the actual recorded to find that lift, and then we calculated that out. We did this for everything, and then we calculated the error associated with the CO actual and CO experimental, and then we've used that information to find the uncertainty of 0.998. For future work, analysis analyzing the weight of each aircraft as it pertains to the major dimension would be highly beneficial, because the weight is similar. The weight coefficient should affect the CO and CD, and it would clarify whether the lift of each aircraft is actually capable of balancing against the gravitational force exerted downwards. Calculating pitch and moment would also be something that we would like to do in the future, but we couldn't due to the fact that it was the instrument that we used to find that information in the wind tunnel was broken and has been for a while now. And the lessons we learned were check calibration before operating wind tunnel, because we went back into the calibration data that we got wasn't really aligned properly, so we had to go back into the wind tunnel after testing to redo that and make sure that we did it correctly, because the group before us apparently made a few judgment errors. And we also would like to conduct our one test and then analyze before proceeding, because as we have it now, or as we did this project, we did most of the experiments before analyzing it, and that would just make everything go smoother and make it so that if we did catch an error, we would be able to catch it before we moved on to the next, and we could not make the same mistake again. And these are our references, and for acknowledgements, we have Matt Turner, the main TA and RTA, that helped us with the wind tunnel and just helping us through this project, explaining different things. And each team member participated equally, I would say. Each of us did our fair share.